Macronix is a leading integrated device manufacturer in the non-volatile memory market. With world-class R&D and manufacturing capabilities, we provide customers with innovative, high-quality, and high-performance ROM and flash memory products. Our products are widely applied in consumer, communication, and computer fields, as well as in the automotive, networking, and other segments. Macronix currently has 3 fabs to manufacture our own brand of memory products. The 12-inch fab can provide the manufacturing technology to below 20 nanometers. Macronix is committed to providing the highest quality products and solutions. We will work closely with our customers to create a new semiconductor era.
Hello, my name is Jim Yastik and I'm a Senior Technical Marketing Manager for Macronix. This is a tutorial on secure flash memory and emerging electronic systems. It is the first of 3 tutorials, and in this tutorial we'll cover security standards, architectures, and features in secure flash devices. I'll cover trends driving a need for greater secure memory, applicable markets and applications, use cases for secure flash memory, as well as general attack types and protection approaches. I'll talk about global standards, frameworks, and platforms driving today's security implementations, as well as modern security frameworks and architectures. We'll talk about flash comparisons and go into details on secure features in flash memory. Modern society is currently experiencing exponential growth of connected devices on public IP networks. In August 2018, IoT Analytics, a well-known market research firm, put the overall number of connected devices at 17 billion and IoT devices at 7 billion. These numbers don't even include smartphones, tablets, laptops, or fixed-line phones. The range of targeted IoT devices could be anything from atmospheric sensors, remote payment systems, IP cameras, smart lighting systems, home routers to connected vehicles. As more devices, vehicles, homes, and things become connected, the threat of attacks is inevitable. The challenge of protecting valuable assets from theft or maliciousness has forced many organizations to devise secure system architectures. Because so much data is being produced, the network architecture is migrating closer to the sensors, either to the premise edge or to the sensor itself. So, store and forward use cases are growing across all industries, driving a need for more memory storage. Then there's the increased affordability of high-performance compute and sensor technologies, the growth of communication networks driving availability of internet connectivity. Good example of this is the growth of 5G networks. Then there's the availability of large-scale data management providers like Amazon AWS, Microsoft Azure, Google Cloud, and then they're driving increased security and secure onboarding requirements. There's also the increasing requirements to meet privacy regulations. A good example of this is GDPR in Europe. There's the need to secure data as a national security requirement, and I think a good example of this is the energy grid. There's a need to thwart internet attacks, for example botnets carrying out distributed denial of service programs. There's an increase in remote content availability and the need to protect against unauthorized use. There's also the growth of buildings being protected with biometric keys for authorized entry and monitoring for unauthorized entry. This is increasing the amount of memory needed for highly secure memory. Then there's the increased instances of corporate espionage, reverse engineering designs to create cheaper knockoffs. All embedded devices could benefit from standard security features in non-volatile memory, and there are a number of markets and applications where advanced features are required. Vehicles being designed that connect to the internet are growing rapidly and being implemented with autonomous features. There are also premium content authentication, electronic payment, user authentication for authorized entry and use, as well as maintenance authentication. Logistics and operation support needs to be secure for shipping industries. Industrial industries increasingly need to measure and monitor operations from central service centers. Enterprise and data centers need to protect against increasingly sophisticated attacks. Protecting the energy grid has become an important topic for some time and is a national security issue. Cellular networks have become critical systems to protect. Medical remote device applications continue to grow as doctors and nurses monitor their patients remotely. Same for increases in telemedicine. And finally, the growth of consumer devices that require authorization and protection of content theft. Here I outline several use cases for advanced secure memory like the ArmorFlash memory device from Macronix. First, the storage of highly sensitive information such as keys, credentials, certificates, DRM or digital rights management. Content service keys, so for example, for audio and video streaming, secure logs or logging, and other PII or personally identifiable information such as biometrics, passwords, contacts, and so forth. Secondly, designs that require a secure data memory and a memory for code storage. And then older designs that need to be upgraded for security reasons without changing the microprocessor or the microcontroller, or microprocessors that do not have secure embedded memory. And then designs that utilize a secure element could combine non-volatile memory and a secure element, lowering BOM costs. Then memory supporting OS architectures that have multiple users such as multi-tenancy or hypervisors that require multiple sets of credentials. Then support for secure provisioning in unsecure manufacturing environments and reprovisioning in the field. Then the protection of firmware rollback and cloning, and the memory that is protected against host device eavesdropping and memory device tampering. Then support for root of trust requirements through unique ID, authentication, and encrypted links. So let's go into the general attack types and protection approaches. There are really three major objectives to achieving secure information in connected devices. The first is integrity. And integrity means that you're trying to maintain and assure the accuracy and completeness of data over its entire life cycle. And examples of that would be secure boot, anti-cloning, authentication. And then confidentiality means that the information is not made available or disclosed to unauthorized individuals, entities, or processes. And examples could be anti-tampering, protocols that guarantee secure data exchange. It could be data encryption or replay protection. And then with availability, we're talking about making sure that the data is available when it's needed. And so you need a good access management design to really kind of protect against denial of service attacks. The table shown below lists some of the more general attack types and protection approaches. To the left here I show some of the more common attack surfaces like communication channels, physical components of the design, the software, or even aspects or phases in the life cycle where a product is most prone to attacks. So with communication channels, some of the more common vulnerabilities are man-in-the-middle attacks, for example, where a hacker studies the bus, inserts a packet that is used to confuse or trick the receiver. And so sequence frames are used along with monotonic counters to solve that problem. You could have a weak entropy source, entropy being defined as a level of randomness. And so you could increase or improve the random number generator, for example, so that it is more random and has higher levels of entropy. You could study the text that you're sending and making sure that any text that is critical is encrypted, or at least use authentication at the beginning of some sort of a communication. Then there are physical attacks, and some of the more common ones are the side channel analysis. Basically studying the physical emissions of the design or timing, and trying to learn more about the system, or inserting faults on the clock or the power lines to glitch it and to see how it behaves, or turning the device off and looking at memory that's left in, looking at data that's left in memory, or brute force, just probing or decapsulating or trying to uncover special debug modes to learn more about it. And so some of the more common protection approaches would be, designing redundancy and fault-tolerant circuits, as well as, hiding or scrambling the bus, or creating a trusted zone and doing more encryption and decryption. Or you could insert a sensor mesh on the top layer of a semiconductor device to essentially detect probing, physical probing, and erase the memory when that happens, or put it into reset. And there are really quite a few other anti-tampering designs. With software, we're talking about, injecting faults. We're talking about rolling software back to a previous version where known vulnerabilities are, so it can attack the system. And then, trying to insert, false interrupts, or creating buffer overflows, or injecting malware, or even, sending, clear text, like I spoke about before up in the communication channels section, over a non-encrypted channel. And so, some of the more common protection approaches here lie around, creating redundancy, or checksums, and then, doing randomization to try to confuse the hacker, and then the use of encryption, decryption, or the creation of trusted, execution zones. Basically trying to create layers of, protection, like compartmentalization, isolation, and really controlling access to the device. And then, of course, root of trust and chain of trust implementations that are pretty well known. And then with lifecycle, we're talking about, some of the vulnerabilities being, them happening right at the very beginning when the device is being provisioned. And so to get around that, to create secure provisioning environments or services. And then code and data being programmed or stored in clear text when really it could be easily encrypted. And, provisioning or reprovisioning in the field really creates opportunities for hackers. And then, there being phases in the life cycle of the product where root keys could be discovered and exploited. And so in those cases, really, we're talking about, root of trust, chain of trust implementations, and the use of public-private key certificates, authentication, and then even in the field using crypto elements that create very secure secret key sharing. Security is a broad subject with many competing specifications and organizations pushing standard implementations. There's a wide range of security standards that differ based on particular technologies, applications, markets, and levels of required security. So for a designer that's given requirements to build a secure device, taking into consideration all these factors really is a daunting task. So where does one start and make sense of it all? To start with, there are specifications, guidelines, and recommendations from governmental agencies. I think the best known in the U.S. is NIST, or the National Institute for Standards and Technologies, for which, like MIPS 140, is well known. And then in Germany, you've got BSI, or the Federal Office for Information Security. But there are many others, like the IETF, Internet Engineering Task Force, or ISO, the International Organization for Standardization. And all these agencies and organizations are focused on general implementations or targeted towards a particular technology application or market implementation. And then there are organizations and industry consortiums that are focused on platforms, and they're usually targeted towards a general area or operating environment. I think some of the most well-known organizations are the Linux Foundation, or TCG, the Trusted Computing Group for Secure Modules. And then in the auto space, AUTOSAR, Automotive Open System Architecture, or SIG, the Automotive Special Interest Group. And then global platforms for secure chip technologies. But there are many others for which, they're leveraged, and it really depends on which markets and applications the product is targeted towards. And then, there are security frameworks that are driven by IP and component suppliers. The most well-known and influential processor IP, I think, is ARM Holdings. And ARM has produced a security framework called the ARM Platform Security Architecture, or PSA, along with associated IP, design tools, software systems that are rapidly being adopted And so terms like trust zone are well known by most embedded designers. And they're single-handedly driving de facto standards and standard security implementations for the embedded industry. But I think it's important to note that their standard implementations, security implementations, are really based on standards that are recommended by NIST, BSI, ISO, IETF, and others. So, they're not doing it alone. And, there are other important security implementations to mention. And I think that the other really important one is the Unified Extensible Firmware Interface, or the UEFI, for which the Secure Boot standard is defined. And that's been driven by years by Intel, Microsoft, and PC makers for securing BIOS firmware, and now found its way and pretty common in embedded designs. And then lastly, there's secure frameworks and secure provisioning processes that target distributed network computing systems, which is one of the foundations for securing IoT devices. And these frameworks and processes are being driven by cloud vendors supplying web management services. Good examples would be Amazon AWS, Microsoft Azure, and Google, the Google Cloud Platform. Several security features, frameworks, and architectures are worth mentioning because they're good examples that have been successfully implemented in today's embedded systems that are commonly found. The first is TPM, or the Trusted Platform Module. The foundation of security is to develop the entire system so that it's a trustworthy entity. Making a device safe from malicious attacks has consequences for system design. The hardware and the software present in the device must work closely to achieve comprehensive, layered security features. TPM, or Trusted Platform Module, was conceived by the TCG and is a well-known standard. And TPM has been addressing the trust issue and related security benefits for PCs, servers, networking gear, and even embedded systems for decades. For resource-constrained IoT devices, TCG developed DICE architecture, or the Device Identifier Composition Engine, with minimal silicon requirements to achieve enhanced security and privacy. Even simple silicon capabilities combined with software techniques can realize enhanced security by implementing a strong device entity, testing software, and safely deploying updates. And then ARM Trust Zone. ARM unveiled the Trust Zone technology aimed at establishing trust in ARM-based architectures during the same period TPMs were being implemented on x86 platforms. Unlike the fixed-function TPM device, Trust Zone privileges certain portions of the hardware and software to construct two orthogonal worlds: a secure, trusted zone for the secure subsystem and a non-trusted zone for everything else. The trusted zone provides a secure environment called the Trusted Execution Environment, or the TEE. The trust zone design extends from the software to all hardware access points. So, for example, a trust zone-enabled AMBA AXI bus fabric ensures that trusted resources cannot be accessed by non-trusted access requests. These two zones share the same physical processor core in a time-slice fashion and do context switching and arbitration either through a software-only implementation for microprocessors or through a combination of software and hardware for smaller microcontrollers. Trust Zone removes the need for a dedicated security processor core and further saves system cost and power by allowing high-performance security software to run alongside a non-trusted operating environment. And then finally, Secure Boot. Along with Trust Zone, trusted software is required. And during the boot sequence, a series of software images are digitally signed with keys generated based on the value of the previous image. This mechanism creates a chain of trust during this booting process on the assumption of a known ROM starting point. This starting point is code that is booted from the on-chip tamper-proof ROM and then accompanied by a root cryptographic key. This is used to verify the next stage of the software fetched from the separate non-volatile memory before handing over control to it. And the key components in the chain of trust are either a key or ROM images. And certificates following the X509 standard are created and issued for the authentication of all software images in a sequence fashion. This includes trusted and non-trusted applications. The complete ROM image is guaranteed by a vendor by using secure provisioning facilities and processes. The diagram to the right illustrates that. So let's go into more detail on the Trusted Execution Environment, or TEE, and secure storage. ARM Trust Zone and Global Platform, as shown to the right, use the TEE concept in their architectural specifications. The TEE is a hardware-isolated or compartmentalized secure environment where the trusted applications can be executed. The TEE offers isolated, safe execution of authorized software and provides end-to-end security. Global Platform's TEE internal core API specification mandates that it be possible to store general-purpose data and key material that guarantees confidentiality, integrity, atomic operations when modifying memory contents. Secure memory may also be partitioned to support multi-tenancy architectures popular in cloud computing. Multi-tenancy supports different users within the single application and operating system. Each one of these users have credentials defining their degree of access to the system, along with application-specific data. These credentials and sensitive application data can only be read, modified, or deleted from the TEE. In both TEEs and TPMs, there's a requirement for securely storing data that is partitioned by application and users. This is particularly true if the OS architecture is comprised of virtual machines or is a multi-tenant implementation. As an example, Global Platform has specified requirements for trusted, secure storage in the TEE internal core API specification. It says that the trusted storage may be backed by non-secure resources as long as suitable cryptographic protection is applied, which must be as strong as the means used to protect the TEE code and data itself. It also says that the trusted storage must be bound to a particular device, which means that it must be accessible or modifiable only by authorized trusted applications running in the same TEE and on the same device as when the device was created. And the secure storage must be able to hide sensitive data or key information when the trusted application itself, and each one has access to its own storage space that is shared among all the instances of the trusted application, but separated from the other trusted applications. And finally, the trusted storage must provide a minimum level of protection against rollback attacks. The top right figure shows the hardware architecture for Global Platform. The REE, or the Rich Execution Environment, has restricted access to untrusted resources, but not the trusted ones. The REE is only allowed to access the trusted resource through services exposed by the TEE client interface. The lower right figure shows the architectural view from a software perspective. This sort of architecture is similar to ARM's Trust Zone security framework. Advanced secure flash devices like the Macronix ArmorFlash provide all the security that is needed by a TEE, TPM, or an ARM Trust Zone. Additionally, ArmorFlash enables a physically unclonable function, or PUF, feature that makes it possible to uniquely bind a memory device to a particular host. ArmorFlash also provides configurable separate secure data regions with independent keys for each region to separately support authentication and encryption. This can ideally be used to control access to each secure data region or user space to support hypervisors or multi-tenant implementations. Let's finish with security frameworks and architectures by talking about secure communication channels and data buses. Communication channels and data buses provide prime opportunities for sniffing or man-in-the-middle attacks, as I spoke about earlier. Fortunately, there are well-known and secure protocols to thwart these sort of attacks. For communications between a host and server, there are several worth mentioning that provide authentication and encryption features. TLS, or Transport Layer Security, is a widely used cryptographic communications protocol standard. It secures traffic among devices with encryption based on a public key exchange or PKE framework. TLS is a layer on top of the TCP/IP software stack. A full TLS implementation requires memory and processing resources that most resource-constrained devices lack. Therefore, for smaller IoT devices, a lightweight machine-to-machine connectivity protocol called MQTT is becoming popular. It minimizes the resource requirements to enable secure communications. The MQTT SN variant can be implemented for most resource-constrained nodes while protecting a form of TLS support. Protecting internal data buses was briefly covered earlier and includes authentication, encryption, data scrambling, hiding data buses under metal layers, and creating redundancy when possible. ARM Holdings' Trust Zone architecture, as an example, extends past the processor core to protect internal data buses by blocking accesses from untrusted applications. Protecting external data buses includes authentication, encryption, data scrambling, and frame sequencing with monotonic counters as a primary means of protecting data buses between a host and a memory device. ArmorFlash provides a good example of this through the use of standardized, proven authentication, encryption, and key sharing protocols to keep external data buses safe for a variety of operations like OTA or over-the-air updates, key storage updates, and read-write sessions. There are three main categories of flash devices. The first is embedded flash. It resides in the semiconductor device itself and is connected to the processor via a parallel bus. The density options for it are quite low because it's a fixed density. However, the information confidentiality, integrity, and security availability are very strong because it's in the device itself and protected. The external SPI flash device is a standard SPI interface, and the density options for it are quite high because the user can choose any number of density options on the market today. However, the information confidentiality, integrity, and security availability are quite weak. And then there are secure flash devices like ArmorFlash that have a standard SPI interface like the external SPI flash. And the density options are high, again, for the same reasons as the external SPI flash. However, the information confidentiality, integrity, and security availability are very strong. It is always assumed that the details of the cryptographic algorithms are well known by an attacker, so it's only the secrecy of the key that ultimately provides security. Trying to keep keys secret is one of the toughest challenges in deploying security. Beside the keys, other user-sensitive or private data are usually stored at the same security level as cryptographic keys. In some secure execution environments, a dedicated secure storage is required not only for the secret key information, but also for the application-specific data. Also, for modern operating system architectures that support virtualization or multi-tenancy, it is a requirement to store and support the security credentials of multiple users for multiple applications. For complex systems, the secret information will be stored in external secure flash memories due to the storage size requirements. The slide here shows a wide range of standard security features that are common in non-volatile memory being offered in the market today. They are effective in protecting various threats to its contents. So why would a product need to implement memory with more advanced security features? Well, to start with, there's an overabundance of existing designs based on older microprocessors. So if there's a requirement to make the product more secure, it is expensive to do major redesigns of existing products, particularly with complex applications in a hard real-time environment that have been field-proven. If a requirement has come from an organization's marketing department that it must now be connected to an open network, where will the required keys and the credentials be securely stored to support the secure access? On-chip embedded non-volatile flash memory is considered relatively safe if tamper resistance has been implemented. But increasingly, general microprocessor suppliers are shrinking the embedded non-volatile memory footprint to only store phase 1 boot code because as technology nodes shrink, say from 55 nanometers to 28 nanometers, the footprint for embedded flash is much larger compared to the CMOS-based processor and other peripheral logic that has to be shrunk. This is because the embedded flash doesn't scale like CMOS-based logic. For example, 40 nanometers is the current stopping point for embedded flash, and so expected overall die size and cost reductions fall short. Also, customers have varying density requirements, so betting on any given customer memory footprint requirement is risky. And embedded flash adds cost to the product that could be shifted to the customer. There are 3 major advanced security memory products available today, and that Macronix also offers: RPMC, authentication flash, and a more full-featured secure flash. RPMC is a memory device whose main purpose is to provide sequencing information for signing digital signatures, and also to provide non-volatile monotonic counters for the host to support sequence frames in secure communication protocols like TLS to thwart man-in-the-middle attacks. Several memory providers currently offer this type of flash as a dual-purpose memory, like Macronix. This means there's a region in flash memory reserved for RPMC functionality, with the rest reserved for normal NOR flash. Authentication flash devices only perform authentication with the host before a secure operation. A good example of this would be the RPMB feature in the Macronix eMMC product. Full-featured secure flash devices perform authentication and encryption along with a full range of additional security features. A good example of a secure flash with advanced security features is the Macronix ArmorFlash Generation 1 product. It is a NOR flash device and has many of the standard security features listed in the previous page, as well as advanced security features listed on this slide. ArmorFlash Generation 1, as an example, has a standard SPI interface and leverages the SPI command infrastructure. It introduces special packet operations that provide secure read and write operations to its secure memory region for data storage. This secure memory region is further partitioned into 16 independent 2 megabit units for data storage. It also has a standard memory area of 224 megabits for code storage that it is accessed directly with regular SPI flash commands after an initial gated authenticated exchange. Let's go into greater detail on advanced security features that can be found in flash memory. ArmorFlash Generation 1, as an example, has the following security elements. First, there is a non-volatile monotonic counter. The use of monotonic counters is the best weapon against replay attacks, even if power outages or glitches occur. This is because monotonic counter values are stored in non-volatile memory. ArmorFlash has 4 independent 32-bit monotonic counters, which only respond to authenticated operations. Counter configurations can be programmed to change counter behavior depending on different application scenarios. Then it has true random number generators, or TRNG. High entropy random number generators are fundamental to almost all secure systems because cryptographic systems depend on secret data that is only known to authorized users. There are 2 main uses for random number generators. The first is in producing a random value called a nonce. It is used in calculating a unique MAC challenge response authentication value. In this case, the client initially receives a random challenge, usually a message embedded with a nonce value from the host. The device uses this value as one of the inputs into a MAC calculation. The nonce value could also be provided by the memory device. The main use of a random number generator, however, is in generating encryption keys. In some implementations, a dynamic session symmetric key is generated from a random number. The TRNG in ArmorFlash has spatial and temporal dependence that produce a random number generator with high levels of entropy. It has a key storage and management system. There is a specific memory region in ArmorFlash capable of storing 4 256-bit keys. Each key is set up through an independent and lockable process. Several key management commands are available to set up keys according to their intended use cases. The configuration allows for separate keys for authentication and encryption operations. Next, there is authentication. ArmorFlash introduces a packet read-write command for various security operations. The packet command is a proprietary link layer packet protocol that is similar to the RPMB protocol. It has its own subcommand operation codes and data structures. The design for the layer above the link layer involves a shared symmetric key used for the authentication process and a cipher block chaining message authentication code, or CBC MAC, which is used to produce the required MAC values. CBC MAC is implemented as part of a block cipher algorithm called CCM, or Counter with Cipher Block Chaining Message Authentication Code. It is a mode of operation of a block cipher algorithm, and it integrates both the authentication of the host and device and encryption of the payload. It is a NIST standard, or NIST publication 838C. And there is data encryption. As part of the AES-CCM algorithm, the data field in the packet contains the encrypted payload based on a symmetric key block cipher algorithm with a minimum block size of 128 bits. ArmorFlash has a unique ID and extra serial numbers. An additional 8K bit secure one-time program OTP area is added for storage of unique identifiers and static data according to system applications demands. The 8K bit secure OTP area further decomposes into 2 rows of 4K bit configurations. ArmorFlash also incorporates an extra 8-byte serial number, which is factory coded and is used in cryptographic calculations to uniquely bond the host and secure flash. And finally, there is a non-volatile PUF, or physical unclonable function. Although programmable unique IDs or serial numbers are okay for identification, a PUF code can be used that is truly unique to each memory device. PUF is becoming common as a unique identifier or digital fingerprint for semiconductor devices. ArmorFlash takes advantage of random and physical variations of a flash memory array to produce a non-volatile PUF code. Users can leverage this code for both identification purposes and an input for key generation. To summarize with key takeaways, the growth of connected devices is generating applications that continue to explode, and along with it, the exponential growth of data. With safety and security, a robust security framework protects against unauthorized actions taken by individuals, while improving safety by incorporating additional controls in the system design. Non-volatile memory requires a range of security mechanisms and policies to ensure identity, confidentiality, integrity, authenticity, and availability. Advanced secure memory storage features found in devices such as the Macronix ArmorFlash is a critical component to achieving security objectives in future electronic systems. And that's the conclusion of this tutorial. I hope you found it informative and increased your knowledge of security. Coming up are 2 tutorials that will cover automotive, IoT, industrial, data center markets, applications, and use cases. So stay tuned. Thank you.